Okay, so this is to give some exam feedback on the Part D of the Evolution of Living Earth exam this year. Just before we start, just to kind of recap some of the things you should be thinking about when you're going into an exam and how to get the most out of it. So you should go through a process. I guess before you even do this, you should probably read the whole exam paper and decide which questions you're going to do. So when you do that, you should read the question, okay, and really try and identify the parts of the question. So although it might be a kind of a big block of text, within that block of text there'll be specific parts of that text which are the things that you're being asked to do. And I'll point some of those out as we go along. Okay, and then it's a good idea to just jot down on the exam, on your answer script, a quick answer that might get you some marks. Okay, and then you can do that for all of the questions. Then you can at least, you've got some marks for every part of the exam. And when you do that, you need to be really specific. Okay, so you need to make sure that you are answering the key parts of the questions that you've identified earlier. You don't want to be answering a question that you've made up, or you're just writing down stuff you know about that topic, okay, because you won't get credit for that. You need to answer the questions that we've given to you, okay, and then you can go back and then you can fill in the details of that answer and try and gain more of the marks answering them in more detail, and we'll go through some examples of that in the next few things. Okay, so this is the first question here. It's got two parts, and we're just going to go through those two parts here. So you're given, in this case, the three equations of the dissociation of, or the reaction and dissociation of CO2 in seawater. You might not always be given these in kind of future exams, so these are kind of equations that you should know anyway. But if we just go on to the individual parts of the question now. And I'll just give myself a pen. In fact, yeah. So you can, if you kind of read through the question, you can see here that it's kind of what are the names of each of the carbon variant species. So that is really what we're asking you. Okay. And then there's a second part of the question that you should answer. What are their relative abundances? Okay. So you've got two parts of the question there to answer. Okay. To get full marks, you need to answer both of them. Okay, so we can just go through here and we can find out the terms in these equations. CO2, so that's got a carbon in it. It's H2CO3, that's got a carbon in it. As does this guy here and this guy here. Okay, so all we're really asking you is to name these things. Okay, which you should know. This is, I'll just give myself now a pointer. So this here is carbon dioxide. This is carbonic acid, bicarbonate and the carbonate ion. Okay, and you should know from the lectures what their relative abundances in seawater are. Okay, so the second part of that the question is worth more marks. We'll just go through and then just highlight parts of the question. So the first part is saying using balanced chemical reactions. Okay, so that's not asking you to do anything, but that's telling you when you do answer, you're going to be required to actually use some chemical equations when you do your answer. Okay. So we're basically, what is the effect of raising atmospheric CO2 on organisms that produce calcium carbonate? Okay. So if CO2 goes up, what happens to calcium carbonate shells? Okay. So atmospheric CO2 goes up producing calcium carbonate shells. Okay. So that's one part of the question, and then a second part of the question is then how does the calcium carbonate, okay, specifically the calcium carbonate, okay, so not other carbon species, not CO2, anything like that, but we're looking for how does the calcium carbonate impact the carbon cycle in the ocean. So we've got two parts of the question again, and you're going to be required to do. Just give myself a pointer again. You're going to be required to because we kind of gave you some of the equations that you're going to need to use. Kind of made this a little bit part of the question. Okay. If you think about what happens here, quite a few people will get this a little bit confused going through it. So when we raise CO2, so if that goes up, we kind of force this reaction to favour this guy, this carbonic acid. Okay, that increases this guy, which should, go forwards to promote more of this, which then promotes more of this. So that, while that is kind of true, okay, but what is not true is that if we increase the CO2, we won't increase everything on the right-hand side of all of these equations by the same amount, okay? And hopefully you remember from the lectures, the reason for this is that all of these reactions, you see, have got a hydrogen ion in them, okay? That means that and they're equilibrium reactions, so they go backwards and forwards, okay? So the more hydrogen ions you have, okay, the more it's going to push all of these reactions towards the left-hand side, okay? And it turns out from the first part of the question is that most of the carbon in the ocean is of this bicarbonate species and a little bit of this carbonate species. So what happens when we add CO2 to the ocean, okay, it goes through all of these reactions and it makes mostly bicarbonate and kind of a little bit of this carbonate as well, which means that when you add CO2 you form lots and lots of this hydrogen ion, okay? That means that the pH of the ocean is going to go down, it's going to become more acidic, and that's going to force the equilibrium of all these reactions towards the left-hand side. So although we've added carbon in the form of CO2, so the total amount of carbon, if you added up carbon, the aqueous CO2, the bicarbonate and the carbonate, if we added all those up, it would go up. We'd have more, but we have kind of moved the equilibrium, so we've moved the relative proportions of all of these towards the left-hand side, so it's favouring less of this carbonate ion and more of this CO2 ion. Okay, so we actually end up, although we've made the total more, we've actually ended up with less of these guys here. Okay, which is kind of counterintuitive, but quite a lot of you got that right, which was good. Okay, so the next part of the chemistry is you need to know what the reactions are when you kind of form calcium carbonate, or more specifically when you dissolve calcium carbonate. So these two reactions here are essentially the same thing. So calcium carbonate, okay, if you react that with an acid, so this is carbonic acid, you dissolve it, okay, and that's kind of quite intuitive. If you've been in the field, you've added acid to limestone, it kind of dissolves. But this is a slightly different reaction to the one you might have done with hydrochloric acid and fizzing off CO2. And this reaction doesn't give off CO2 because the reaction, in fact, produces basically dissolved ions of calcium and this bicarbonate ion. Okay, so the non-fizzy versions, basically. And this second reaction at the bottom is essentially the same reaction at the top, because you see there's a backwards and forwards reaction over here between carbonic acid and CO2 and H2O, and that's reflected here. You can basically just switch between these two versions of the equation very easily. So if you think about if you're adding CO2 to the system, we're making a little bit of this, although it's kind of in equilibrium backwards and forwards, which means that we're adding something that will dissolve the calcium carbonate. So that's going to force these reactions this way. So by adding CO2, we acidify the ocean, we make it more likely that calcium carbonate is going to dissolve, and that's what's kind of the first part of the question up here. So the other aspect of this is what happens when that calcium carbonate does dissolve. Okay, so we've got these other things that happen. So when we do dissolve it, we're adding bicarbonate to the ocean, but we're not adding hydrogen ions. So you can see that we're adding basically alkalinity to the ocean. Okay, and you might want to think about what that does in terms of the buffering capacity of the ocean. Okay. Other things that you might want to consider is that when calcium carbonate organisms or organisms that produce calcium carbonate, when they produce these shells, so if we think about this in terms of the bottom reaction now, those organisms are taking dissolved calcium and dissolved carbon from the ocean, and they're forming calcium carbonate. So whenever an organism forms a calcium carbonate shell, it will release CO2 into the water. So it's a little bit counterintuitive. So you think if something's producing calcium carbonate, that should be kind of locking up carbon dioxide out of the atmosphere because it's making something that's made out of carbon, okay, and taking it from the ocean and putting it into the sediments. But in fact, that process releases CO2 into the water, which can then kind of equilibrate with the atmosphere. So one of the things you might remember from the lecture is the inorganic carbon pump, which is if you have lots of organisms that are producing calcium carbonate, that's a net flux of CO2 to the atmosphere. So these are things that you could be thinking about in this kind of question. Okay, so moving on to question 2. So this is a 3-parter, so you can kind of just look just briefly. There's a first part that's worth 40%, a short second part which is worth 20%, and another 40%. Okay, so we're just gonna go through those processes out, and I'm just gonna give myself a pen. Okay, so the key things to look at in this question is this first word here. So the first word is describe. Okay, so this means that we're not just looking for a list of things. Okay, we're wanting you to actually write something a little bit more substantial, and that's kind of reflected in the mark over here. Okay, so we want natural and anthropogenic ways which nitrogen can be fixed. Okay, so this is kind of it. So you could have thought quite easily that nitrogen fixation. So this is the taking of the totally inert N2 gas, and then the process of fixing into either ammonium-based form or a nitrate-based form. Okay, so there are basically 3 ways of doing that. So that happens in lightning, it happens in biotic fixation, and it happens in kind of when we do kind of industrial fixation, when we do the Bosch-Haber process and that kind of things. Okay, so those are the things. So if you're doing your quick and short answer, you could just jot down those 3 terms: lightning, biotic fixation, industrial or Bosch-Haber process. Okay, and then move on, and then come back to that question later on. Okay, and you've at least got some credit for that. Okay, but then the key part of the question here is to describe. So what we're also looking for is a description of each of these processes. So what is it about lightning that enables nitrogen fixation to happen? What is the chemical pathway? Okay, so you could maybe embellish that with some kind of equation. Similarly for biotic fixation, what is it that actually does the fixation? Okay, you might want to embellish on maybe what kind of environments that happens in. And similarly for the industrial, what are the pathways? What are the conditions required? Things like that to really give a full answer. I would just make a little note here that quite a lot of people kind of went off on a bit of a tangent and started to describe all of these other kind of processes here of nitrification and denitrification, and how these kind of made bioavailable forms of nitrogen, which is kind of, they do make bioavailable forms, but the key thing is this word fixed here. So nitrogen fixation is a very specific term that refers to this process here or this process here of taking this really inert N2 and making it useful. Okay, so deviating, this is where we need to be really specific with our answers. Okay, so the next part of the question was a very short one. So the question is, why is the surface ocean concentration of nitrate so low, and how is the productivity maintained in such a low a nutrient environment? Okay, so there are 2 parts. So why is the surface ocean concentration low? Okay, and if it is low, how can life still happen there? Okay, so we're really looking at. So this is as a profile here. I'll just go back to pointer. So we've got a profile here of depth in the ocean and nitrate concentration. Okay, quite a few people kind of were talking about nitrogen diffusion in and out of the atmosphere, but the question is specifically asking about nitrate, so that wasn't very relevant. So we've got utilization in the surface ocean, and you might want to then embellish later on as to why we get utilization in the surface ocean, not the deep ocean. Okay, and then once we've removed most of the nutrients, how do we keep life going? Okay, so how do we kind of resupply or restock those nutrients into the surface ocean? Those are the things that needed to be answered in that question. Okay, now the second part of the question wasn't answered, or sorry, this third part of the question wasn't answered so well. So again, we'll just have a look at reading this here. So some regions of the oceans do have high nitrate concentrations. So even when they're far away from the nutrient inputs from rivers. Okay, so the first part is a statement, and then the second part, let's get my pen back. Okay, so I want to know, where are they? Okay, so this is kind of a geography exercise. I want you to tell me where these places are. Okay, and what I specifically want to know is, why are the nutrient contains not depleted? Okay, so part of this could be, why is the supply of nitrates to these regions very high? But the question specifically asks is, why are those nutrients not being used? Okay, so if you kind of maybe remember back to the lectures, this is a map of surface nitrate concentration. Okay, so you can see here that there are regions. There's the North Pacific here, Equatorial Pacific. These are really large regions of the ocean that have got very high nitrate concentrations compared to the blue of the rest of the ocean, which is kind of the typical surface ocean where almost all of the nutrients have been taken away. Okay, so you can see that there are some places around the Earth, so it's quite a lot of people picked out places around Namibia, Arabian Sea, Equatorial Atlantic, where there are slightly elevated concentrations of nutrients, and these are places where nutrients are being brought up to the surface. So the supply of nutrients is here, it's very high, and therefore the biological activity can be sustained. Okay, but the question goes on to ask, why are these places not being kind of like completely, why are these nutrients not being completely used up? Okay, so hopefully you'll remember back to the lectures, there's these things that can limit for the nutrients to be used up. You have to have life going on in the surface ocean, and if there's something that stops the life happening, okay, so for instance, if you took all the nitrate away, you would stop the life happening. Okay, but in this case, we're not taking all the nutrients away. There might be something else missing. Okay, so in this case, maybe in these high polar regions around Antarctica, in the Pacific up here, it might be too dark in the winter, okay, for enough photosynthesis to happen to use up all of the available nutrients. Or there might be other nutrients that are required for life, maybe phosphorus, maybe micronutrients like iron, which if you don't have them, then you can't use up the nutrients. So even though there are little phytoplankton that are ready and raring to go, but they can't photosynthesize because they're missing key nutrients. Okay, so that's kind of one aspect that you could have taken on the thing. Okay, because the question is specifically asking, you see, why are they not depleted? Okay, so the last question, question 3. Quite a lot of people had a crack at this guy. So we'll just go through this. So that kind of the first part of this question, okay, it's very, very kind of quick and easy. So what is the definition of resonance time? So we're basically just asking for a definition. Okay, and if you remember back to the resonance time kind of lecture, there was also a short video on this. I mean, it gives you kind of the answer here. So it's basically the time given for an atom that spends in a reservoir. So it's basically if stuff is coming in, okay, in maybe a river, it goes into the ocean, okay, and it's gonna go around here for some time before eventually it's exported out, either to the sediments or to some other output flux. Okay, so it's basically representative of that time. Okay, so it's actually the average time, because some atoms might go straight through, some might go round and round here for a very long time, but we're really looking for that kind of statement there. Okay, and you could have embellished that kind of with an equation. That would have been totally appropriate, as long as you define all the terms in your equation. So that's what we're looking for. And then the second part. So this part was universally answered extremely poorly. And I'm not entirely sure why, because you've mostly got all of the way there. got kind of a little bit lost in some of the details. So we have some information. So I'm just telling you that the concentration of phosphorus in the deep ocean is this number here. Okay, grams per litre. Okay, and I tell you that the volume of the ocean, okay, is this kind of extremely large kind of volume. And the riverine flux in terms of grams per year is this. Okay, okay. So the question is asking you just to calculate the residence time of phosphorus in the ocean. Okay, so we've got our equation from before with the residence time, and it's the mass divided by the flux. Okay, now, so mass, flux. Now, importantly, okay, it is not the mass of the ocean. Okay, it's the mass of the thing that you're interested in the ocean. So in this case, to work out the total mass of phosphorus in the ocean, we have to times the concentration by the volume. Okay, and I did make this slightly tricky, okay, because I've given you the concentration in grams per litre, okay, and I've given you the volume of the ocean in kilometres cubed. Okay, so to work out the amount of grams of phosphorus, we just need to times the concentration by the volume. That's concentration times the volume. Okay, but to make sure that everything's in the right units, it's kind of would be a good idea to convert everything into something like, maybe if you convert everything into, well, convert this number into the number of litres in the ocean rather than the number of cubic kilometres. Okay, now quite a lot of you realised that you had to do that. Just made a small kind of like arithmetic mistake when you did so. So there are the easiest way to think about doing these calculations when you're converting kind of units and stuff like that is not to think of terms of how many litres there are on a cubic kilometre, because that's quite hard to think of. You think of, well, a kilometre is 1,000 metres along its side, okay, and a litre is 10 centimetres by 10 centimetres by 10 centimetres. So it's a cubic decimetre. Okay, so if you think how many decimetres there are in a kilometre, okay, there are 10,000. Okay, so that's 10 to the power of 4. Let's write that down here. 10 to the power of 4. Okay, so that's how many 10 centimetres there are in a kilometre. And then because we're going in our units are cubed, if we just cube that whole lot, okay, if we just cube that whole lot, that's what we need to times this number here by, okay, to get the volume of the ocean in litres. Okay, so this is the same as, that's the same as say 10 to the power of 3 times 4, so that's 10 to the power of 12. So so we would now have 1.35 times 10 to the 9 times 10 to the 12, which is equal to 1.35 times 10 to the 21. Okay, just add those things together. Okay, and we could then put that in here, so we then have our concentration times 7 times 10 to the minus 7 times 1.35 times 10 to the 21 divided by the flux, which is 3 times 10 to the 11. Okay, and hopefully you go through that and you end up with something 3,000 years. Okay, now to get full marks on a thing like this, obviously you have to have the right units. Okay, and the units of a residence time will be a unit of time, so you could convert this into SI units, into seconds or into kiloyears or whatever you're interested in, but it has to be at least a time. And the other thing to think about is the number of significant figures. So I have given you information here to 1 significant figure, to 3 significant figures, and to 1 significant figure. Okay, so if you're doing a manipulation with these numbers, okay, you're never going to be able to get an answer that is going to be better than one significant figure, because that's the precision of the data that you're given. Okay, so I think the actual answer is 3,100 and something years. Okay, but because we don't know these input values here very precisely, okay, we don't know our answer very precisely. Okay, so I'm only quoting it to one significant figure. So you should have. I don't think anybody quoted it to the right number of significant figures. But anyway, so you should do that. Okay, and then the last part was obviously very hard to answer because quite a lot of you didn't get sensible numbers. I think the most wrong of the answers was at least I think 35 orders of magnitude out, which is so different it doesn't even have one of those kind of prefixes like milli or micro. It's just such a big difference. And hopefully when you do these questions, if you come up with a number which is the residence time of something in the ocean that's kind of shorter than at least a second, you should think that you've maybe done something wrong and recheck your calculation. Which is always a good thing to do when you're doing kind of calculations on kind of the Earth. So the thing to this last question, going off that little bit of a side there. Okay, so we're basically saying what assumptions do we make? Okay, that's one part. Okay, and then we need to reconcile our answer with the low surface concentration. Okay, so that does kind of hint that our answer should suggest that the surface concentration shouldn't be very low. So our residence time is 3,000 years, which is kind of a similar timescale to the mixing timescale of the ocean. So the amount of time it takes, so there's this different concept to the residence time. We're talking now about the mixing time. So the amount of time it takes to even out the concentration. If we just put some imaginary dye in the ocean, how long would it take for that to be kind of well mixed in the ocean? And that would take somewhere between kind of like 2 and 10,000 years. So if we have a residence time that's similar to the mixing time of the ocean, we wouldn't expect there to be huge variations in concentration in the ocean. Okay, and we've worked out the residence time of the deep ocean to be about 3,000 years. Okay, but we know that the concentration in the surface ocean is very different. Okay, the concentration in the surface ocean is essentially zero in most places. So that means that there must be something else going on in the surface ocean. Okay, so we can think about that in terms of residence time. Okay, so you should be thinking about making an answer and saying, is the residence time in the surface ocean going to be longer or shorter than the residence time in the deep ocean? Okay, you might also want to think about why that might be. So what are the magnitude of the fluxes in and out of, or in and out of the surface ocean and the deep ocean, kind of between the two, in fact, relative to the fluxes in and out of the whole ocean. Okay, so these are things that you might want to be thinking about. Okay, and the other thing is that we need to think about the ocean as these two separate boxes, because we've got kind of a surface ocean, okay, that is kind of density stratified, so it's kind of, you can think of it as a different box to the deep ocean. Okay, deep ocean is another box. And here, where you don't get much variation in the concentration, you might get some, as we have some slow addition from remineralization, but we get lots of changes in concentration in the surface ocean. Okay, so you want to think about answering. That's basically the second part of the question, and the first part of the question was this: what assumptions do you make? So again, this could be some of the things we think about when we're calculating residence time. Does the flux in equal the flux out? Are we at steady state? Those are things that you think you should always be thinking about when you're asking a question that asks you what the assumptions are. Also, sometimes you're not specifically asked what the assumptions are. If you're just asked to define something, for instance, what is the residence time defined as? Once you've answered your quick answer, you could go back and embellish that later on if it didn't ask you, in this kind we did ask you what the assumptions were. If it didn't ask you, you could add those assumptions in, and that would almost certainly give you kind of good credit. Okay, so